Hello, everyone. Hello, online. Y'all should be pumped today, last day before, well, for this class before spring break. We'll probably have more classes later today or tomorrow, but it's getting close. It's supposed to be cold this weekend, but then get warm. So I think your spring break actually will be a pretty spring break. So I hope you have some time to enjoy it and don't have to do too much classwork or have to work, pay work. Well, speaking of work, so you do have some homeworks due. These are pretty short though. This one is a little bit longer, but most of the problems are pretty straightforward. The trig functions of angles. So that's due tomorrow. So don't forget about that, right? And see now you can tell from the title of this homework, right? These trigonometric ratios that we just thought of ratios from right triangles, right? Sine, cosine, tangent. Now we've changed our terminology. We're calling these functions now. We can think of them as functions with much larger domains. Now that we know how to compute the sine and cosine, et cetera, for angles, that are negative or larger than 90 degrees, right? That's what this homework is all about. And that's the business with finding a reference angle, right? And then using the reference angle to compute the trig functions. On this, so the way I was showing you guys how to do that, right, is by drawing the angle, right, in standard position, and then just looking at your drawing and using that to find the reference angle. But you can actually do this a little bit more methodically. And that's the point of, I don't know if I can see that at home. I didn't bring up the PDF, but this is the printed version, that has the table of special angles on it, right? And on the third page, there is actually kind of a step-by-step process for finding reference angles. So if you're a little bit impatient with or not comfortable, I shouldn't say impatient, but if you're not comfortable with finding reference angles by drawing the angle and then looking at your drawing and then finding the reference angle from the drawing, you might follow the guide here when you're doing that homework that's due tomorrow, right, for computing reference angles, because this does it kind of methodically. But I think this is actually more difficult, but for me it is, but your taste might be different. So that's why I included that in this handout. So keep in mind you've got that if you want to refer to that when you're doing your homework for 6.3, right? That's due tomorrow. Okay, so I'm not going to go through the steps on this handout because we practiced doing reference angles now quite a bit. So I'm going to go through those steps. They are there. Don't let me forget to pass out the homework. Now these other two topics are things that we've been talking about, right, since the test. So function direction and average rate of change, these are sort of special topics in functions, advanced features of functions or advanced topics in functions. And the reason that we're taking this little detour here back to talking about sort of functions in the abstract is we're going to circle back and apply these ideas to the trigonometric functions, right? So the things that we learned about function direction and things we learned about average rate of change, we're going to circle back and apply that to help us understand better the trig functions, okay? When the trig ratios, when we think of them as functions. So that's the same thing for this topic today that we're going to talk about, which it doesn't have the homework for it yet, called transformations. And this is especially useful in help us understanding trig functions. So we'll get to that in just a second. Do y'all have questions though? So don't forget that homework that's due tomorrow. Everyone needs to, since the first test, right? A lot of you need to really keep your homework average up. For some of y'all did BAFO on the first test, and so you're under a little bit less pressure. But for many of you, make sure that you're keeping your homework average up, right? To help compensate if you had a lower test score on test number 1 before you get test number 2. Of course, that's the second way for raising your average. Okay. Forgot if there was something else I was going to say. I am going to post a homework on this topic today of transformations. So be looking for that, but it won't be due till after spring break, right? What's due on spring break is just these things that are posted here, right? And these are not super lengthy. Oh, I did want to remind you, remember, in these two homeworks, I'm not sure if it's included or necessary for the homework that's due tomorrow, but in these two homeworks, right, sometimes it's helpful to draw graphs. So don't forget that if you don't have a graphing calculator, that's fine. You don't need one because at the top of the homework, it'll either be under instructions or there's another. There are two things that I can post with a homework. One of them is called instructions, and the other one is I forgot. It's like directions. It's almost the same as instructions, but I don't see it here. So anyway, look at the top of the homework. You may have to expand these categories here, but once you do, somewhere there you should find a link to remember this screen, which you can use for making graphs, right? So you don't have to have you can do this right. You can make these graphs right from your homework, and you don't have to have a graphing calculator, but a graphing calculator is fine too. So if you want to use your graphing calculator, that's great, right? So remember, on some of these problems, it's going to say, we practiced this last time, right? It's going to say, use a graphing device to draw a graph, right? So of course, that could be your graphing calculator, but it could also be this web page that you have the link to, right? So, okay, so just don't forget about that. That's available to you. Okay, then I don't really think I looked at average rate of change this morning, so it doesn't seem like you need to make any graphs in average change. Okay, but I'm pretty sure the transformations homework that I'm going to post, you'll need to be making some graphs because that's all about graphing. Okay. All right, so much for that. Do y'all have any other questions from this, right? Okay, well, good luck with that. So, and again, as usual, you can email me, but keep in mind, right, if you're doing it at the last minute, I may or may not respond. So, depends on where I'm at and what I'm doing. It's hard for me to answer you from my phone. I can answer you from the phone, but that's really clumsy. So, I'm not sitting close to my computer, may not get a response very quickly. Thing else I was going to say. Oh yes, so if you want to, don't forget, if you want to request an extension, that's fine, you can do that, but wait until after the due time. Okay, so don't email me prior to the homework being due. All right, so sometimes I get extension requests at like 11:30 p.m. but the homework is not really due till midnight, right? So wait until afterwards, because then you'll get it automatically. But if you ask beforehand, it's going to come to me. Okay, so save your extension request for later. Okay. All right, so let's go ahead and switch to the now to the notes. So let me find them, and as per our usual practice here, I got something for you to do to start with. So it's kind of easy, but this is a little bit of a complicated graph. So see if you can write down for me where this function, so this is just an entirely made up function, right? Just for this question. But where is this function increasing and where is it decreasing, and then where is it constant, right? Remember, you're going to give your answers in terms of the intervals, right, along the x-axis. Remember, always give your answers here as sets along or intervals along the x-axis, right, not the y-axis. Have a stray mark here. Let me erase that. Okay, so can y'all see that sort of well enough to make a decent stab at identifying where it's increasing and where it's decreasing? And in this case, where it's constant, which is kind of unusual for graphs, but I threw that in there just so I could ask that. while y'all are doing that, I'm going to lower the screen. So you guys at home as well, right? Take a look at that graph and just identify those things. This is what the function direction homework is, just lots of questions like this. So this is good practice for the function direction homework, but also gives you a chance here to remember what we talked about last time. Well, I also said identify the local maxima and local minima if there are any. But you can say that for last after I've identified where it's increasing, where it's decreasing. So remember, you're doing this from the graph, so you're just going to have an estimate, right? So you just have to kind of look and give it your best guess. Okay, so let's start with increasing, because we're going to use that for, I have a part B here that's obscured. We're going to use this for part B. So let's start with increasing. Where is this curve increasing? Right, perfect. Minus
Let me just quickly
3.
tell the professor, like,
-3 to -1, right? Yeah, perfect. Right. Because as we go from left to right, Iris, you can see it, right? There, the curve is going up, right? In other words, as the x values increase, the y values are also increasing as well. So remember, we're always thinking of moving from left to right. So we're always thinking of the x values as increasing, right? So the question here is, as we move from left to right along the x-axis, where are the y values going up, or where are the y values going down? Right? What about decreasing? So that's a little bit more complicated, right? Because there's several places where this is falling. Hi, Robbie. Yeah, I hardly never. You're almost always in class. Since I have you there, Robbie, can you hear me?
yes, I can.
Okay, Robbie, can you see here where this is decreasing? You can just tell
Sure.
me. Yeah.
It is decreasing from negative infinity
Right.
to -3 on the x.
Yeah, from -infinity to -3 on the x-axis, and then where else?
It looks like from -1 to 1.
From -1 to 1. Yeah, perfect. So
and then from 3
to 1, and then also what?
From 3 to positive infinity.
Right, perfect. 3 to positive infinity. So decreasing there in several places, right? And so we'll combine those intervals with our union operation, right? So we get technically one set. When you combine these intervals with the union, you get one big set. And there it is. Okay, so this one, this curve now does have a place where it's constant. So again, as I mentioned, that's kind of unusual, but it does in this case. Where is it constant? Starts where, Emil? -1 to 1. No, that's going down, right? So that's decreasing.
Oh, it's not
Yeah, but where is it steady? Go ahead. Starting at 1, right, and continuing to where, Emil? 3. Perfect, right. Okay. So see, a constant function is going to be a horizontal line. All right. So this graph is a horizontal line right here from 1 to 3. Okay. Did y'all get that pretty easily? That's about as complicated as they get. Okay, in terms of, have lots of has lots of oscillations in it, right? So if you can write that one down, then probably going to get the homework really easily and do well on the test. Okay, on this. So remember, we don't have really any tools for right, at our disposal for answering answering questions about function direction. That's what I call this topic, function direction. We don't have questions. We don't have tools for answering questions about function directions, except for making a graph. Okay, so in calculus, you will learn, as I mentioned last time, right, how to determine function direction without actually having the graph in front of you. Okay, so you'll be able to do this analytically just from the formula for the graph. Okay, and that way you'll also be able to get exact answers, not just estimates from looking at the graph. I forgot the second part here. So where do we have any local maxima? That's the plural of maximum. Or where do we have any local minima? That's the plural of minimum. So do we have a local maximum here in this picture? So remember, that is a local maximum is a peak turning point. So do we have a peak turning point here? Right, yeah, right there, right, okay. So we have one at x equals -1, right? And I think that's supposed to be y equals 3 is the y coordinate. So we can estimate that. So we have a local max there. And so you can either write the coordinates of the point as the local maximum, but technically the local maximum is really the y coordinate there, which is 3. That is not an absolute maximum. So in the homework, they may ask you, do you have an absolute maximum? Absolute maximum would be a maximum y value that is global. In other words, it's the maximum y value for the entire curve. But the 3 here is not the maximum y value for this entire curve, right? Okay, because over here on the far left, eventually the curve goes above y equals 3. So you really don't have an absolute maximum in this picture, in this graph. Okay, over here on the left, the graph extends up to positive infinity on the y-axis, so there is no maximum y value. But in this region, okay, in this just this little piece of the graph, the maximum y value is 3, right? Okay, so that's why it's called a local maximum. What about local minimum? So do we have any valley turning points? That's what you're looking for. But yeah, Amanda, so this is a point, right? So it's not a set. Yeah. Yeah, -3 and 0, right there at here. Okay. So you have a valley turning point there. That counts as a local minimum. But again, not an absolute minimum, because 0 is not the lowest possible y value, because over here on the far right, eventually the graph goes below 0, right, on the y-axis. So this is only a local minimum value, not an absolute minimum value. Now, there are 2 other points on the graph that students might identify as local minima or local maxima. It looks like we have a turning point here and also a turning point here. These are not turning points, okay? So that, they are kind of, visually important points on the graph, but they do not count as turning points. To have a turning point, the graph must switch from increasing to decreasing or vice versa, okay? Here, the graph switches from decreasing to constant, not increasing. So this is not a turning point. And this is also not a turning point because the graph is switching from constant to decreasing. It would have to switch from increasing to decreasing to have a turning point. So, these are interesting points on the graph, but they do not count as local maxima or local. So these are the only two that we would identify here in the question, okay? Now that we know that this function is increasing over this set, right? From x equal -3 to x equal -1, I'd like to know how fast is it increasing over that set, okay? So that's my next question. What is the average rate of change where the function f is increasing, okay? So how do we measure how fast that curve is increasing where it's increasing, right? From x equal -3 to x equals -1. So the way we answer that question is by using this quantity called the average rate of change, right? Okay, and so that's what I want you to compute here, the average rate of change where it's increasing. Do you all remember the average rate of change formula? It's the same as the slope formula, right? Here's the way we wrote it down. It looks a little bit different from the slope formula when you write it in this context, but it really is the same as the slope formula. It's f of b minus f of a over b minus a. This is really rise over run, okay? All right. Just expressed a little bit differently than in the slope formula. So see if you can compute that average rate of change for me. Remember, this is this. What did we say the coordinates of that point were? -1 and 3, right? Okay. So this is -1 and 3, and this is -3 and 0. And in your average rate of change homework, you're going to get to do this several times. Most of the times we'll be using a formula, but here you're just going to be using the graph. Okay, so all right, so let's try this. Someone someone at home there on Zoom, you can, if you would, chat in for me what the answer is. Okay, so it's just a numerical answer, right? So just chat in for me the answer. I know we've got lots of smart people there on Zoom, so I know y'all got something that you can tell me. Remember, the average rate of change formula is a slope formula, right? And so remember, we really are calculating the slope of a line. It's going to be, in this case, the slope of the line that connects these 2 points, because that's where the curve is increasing, right? From x equal -3 to x equal -1. So what we're really doing is just calculating the slope of this straight line that connects these 2 points. But remember, the curve is not quite a straight line, right? Okay. But in computing the average rate of change, we're going to treat the curve like it's a straight line connecting these 2 points. Okay, so that's not exactly accurate, right? Okay, that's how we're going to try to measure that rate of increase there, where that function is increasing. So what do we get? I'm still waiting for someone to type it in. Someone chat that for me on Zoom. Got all kinds of smart people out there. Ahmad, Christopher. If I don't call you out, doesn't mean you're not smart, but I know I have several out there. Kenneth. There it is, Ahmad. I don't have to repeat it. It's written. Okay. Where is it in, what's the average rate of change where it's increasing? Okay. So that's going to be a number. There's the formula. Someone else on Zoom? Mr. Aguilar, are you there? Christopher?
I'm sure if I got it right, though. I got one.
You got one?
Yeah.
Oh, okay. Well, let's check it then. All right. So, so let's see there. So tell me there what you filled in here to the. Tell me there what you filled into the formula.
Is it for B is a -3? I'm not sure though.
Okay. Yeah. So that's a good question to start with. Is what is the A and what is the B? So we want to find the average rate of change from x equal -3 to x equal -1, right? Because that's where the curve is increasing, right? From -3 to -1. So the A value is going to be usually, that's the smaller of your two boundary values where you're calculating the average rate of change. So the A here would be the -3, Christopher, and the B would be -1. All right. Okay. So with that in mind, Christopher, what is f of b? So remember, this is the f of b means the y value, right? So what's the y value when x is b, which is -1? Just read it off the graph there.
F of B would be -1.
No, b is -1. So what's f of b? See, b is -1. Let's fill it in here. We have f of -1 minus f of a, which is -3, right?
Yeah.
So what's f of -1? F of -1 is, what's the y value? See, f of -1 means y value, right? So what's the y value when x is -1? What do we see on the graph there?
3.
3, yeah, sure, right. Okay, so this is just 3. All right, now with that in mind, Christopher, what's f of -3?
0.
0, yeah, okay, right. And then now just fill in the values in the bottom. We said what, b was -1 and a was -3. So just plug those in. Be sure you get all those minus signs because there's a lot of them here, right? B is -1, A is -3, and then this minus sign is part of the formula, right? So you end up with a bunch of minus signs here. So altogether we have what, 3 over. So Christopher, what's the denominator going to end up being?
2.
2. So you don't get 1, Christopher, but you get kind of close to 1. You get 3 halves, 1.5. All right. So did y'all get that? What's the average rate of change? 1.5. Okay. All right. Robbie said minus 3/4. Sorry, Robbie, that's off by quite a bit there. All right. Okay. So wrong number and the sign is wrong too. All right. So 1.5. Okay. Is the average rate of change. We know this had to come out to be positive because we can see that because the function is increasing here, right? You know, the slope of this line has got to be positive, right? So if you came out with a negative value, that's immediately a check for you that something has gone wrong, right? Okay. Have to get a positive slope here for this line. By the way, what's that line called? What's the name for that line that connects 2 points on a curve? That's a secant line, right? Okay. So 1.5 is the slope of this secant line. Right now, what is that? So what is that 1.5 telling us? Remember, it's telling us what it's supposed to be telling us is how fast that curve is increasing. We know it's increasing, right? But how fast it's increasing from from x equal minus 3 to x equal minus 1. That's a measure of how fast the curve is increasing. So how do you explain that to your grandmother? You would say what? Well, the average rate of change is 1.5, right? Okay. But I kind of already put that up here, right? Okay. Fernando, all right. They already have average rate of change is 1.5, right? Okay. So I'm looking for a little bit deeper explanation than just saying the average rate of change is 1.5. So how do we explain our result here? You would say on average, be sure you start off with the on average because this curve is not a straight line. So this rate of change is not steady. Okay. This rate of change is not steady. So to distinguish this curve from a line, you would say on average, all right? On average, and now let's see, where are we computing our average rate of change from what? X equals what? -3 to x equals -1. We have to be very careful and stipulate where we're computing this average rate of change because again, this curve is not a straight line, all right? So this average rate of change only applies to this portion of the curve from x equal -3 to x equal -1. Other places on this curve, things are working differently, right? In fact, in other places on this curve, the curve is not even increasing, right? Okay, the curve is decreasing, right? So we have to say it's our average rate of change is just for this part of the, of the domain, okay? And now what's happening from x equal -3 to x equal -1? You can say the function, or you can say the curve, or you can say y if you want to. That's fine. All right. What's happening to our y values? Y is doing what? Increasing, right? Okay. By how much? That's where the average rate of change comes in. Okay. Y is increasing by 1.5. All right. When what occurs? Yes. Right. When x increases by 1. Remember, in an average rate of change, just like in a slope, the x is always increasing by 1. Okay. So for this little piece of the curve, y is going up by 1.5 when x increases by 1. That's correct, right? Okay. So on average, if you go from -3 to -2, it goes up by 1.5, and then you go to -2 to -1, it goes up by 1.5 again, and that brings you up to 3. Okay. So that seems very obvious from the picture, right? The meaning of the average rate of change. Okay, right. So there's your little brief review there of average rate of change. For those people who weren't here last time, then well, there's your brief introduction there to average rate of change as it applies to curves instead of straight lines. Okay. All right. Now let's switch to today's topic, which is going to be what's called transformations. So the point of transformations is, again, graphing is a clumsy and can be a complicated process for curves other than straight lines, right, or other simple types of curves. So transformations is a tool that we can use to help us again understand what a graph looks like, or how to make a graph easily before we make the graph. Okay, so it gives us a way of visualizing what a graph looks like, or what it should look like before we actually construct the graph, whether we're doing that by hand or if we're doing that with some other software. Okay. So furthermore here for transformations, what transformations does is, if we know some simple graphs, or if we know the shape of some graph, say we already have graphed some curve, so we already know what it looks like, then transformations allows us to use that information to maybe graph more complicated curves that are similar to, but not exactly the same as the curve that we're starting with, right? Or that we already know the graph of, right? We'll see plenty of examples of this in just a moment, and so you'll know better what I'm trying to tell you. Okay, if it seems a little bit vague now. All right, so I'm not particularly fond of the way the book presents transformation, so I'm gonna kind of elaborate on the way the book is going to present it. All right. By the way, so the answer to this question in the margin here is what I just said. How is knowledge of transformations helpful? That's going to help us in understanding what the graph of a particular curve should look like before we construct the graph. Okay. All right. So suppose you have a function, right? And so this is just an arbitrary function. It's called f of x. All right. And so maybe you are, so this could be any sort of formula, but imagine you already know what the graph of f of x looks like for some reason. Okay. So it may be some graph that you've already constructed, or it may be some simple function that, you can just look at it and say, oh yeah, that's a simple curve, so I know what that graph should look like, right? Then it turns out here that you can, there's a couple of simple ways, all right, that you can transform that graph, or you can transform that function to another function. And if the, I'm not saying this right, okay, all right. If you change the formula for that function in certain prescribed ways, okay, then you also know how the graph of the function is going to change as well. All right. And there are sort of three basic categories of ways that we can change functions, that we can alter the formula for a function, so that we can know very easily what the graph of that altered function is going to look like. All right. This first category of change, these changes are called transformations, are called shifts. So there are two types of shifts here. All right. That's why I have A and B here surrounded by the curly brace. Okay. So these first two transformations or changes that I'm going to mention here are called shifts. All right. So let me go back to where I was a moment ago. All right. So suppose you have the graph of a function. All right. And you know already what the graph of that function looks like. Then if you simply change that formula by adding or subtracting a constant from that function, that is going to also, of course, change the graph, correct? But it's easy to know how the graph is going to change. It's this adding or subtracting this constant is just going to shift the whole graph up or down by this many units, okay? That's why this is called a shift. All right, so let me repeat here now what this first transformation looks like. So you have the formula for a function, and you add or subtract a constant from that formula. This has to be a constant, so it cannot involve x. All right. So you have a formula for a function. Of course, that involves x, right? But if you just add or subtract a constant from that formula, the only way you're going to change the graph of that function is shifting it up or down by this many units. If you add the constant, you're going to shift it up. If you subtract the constant, you're going to shift it down. Okay, so the whole graph either moves up or the whole graph moves down. Just that simple. All right, that's one type of shift. Now, the second type of shift looks very similar, okay, because it also involves adding or subtracting a constant. All right, but I want you to notice where the constant has been added. Okay, here, notice we're adding the constant to the entire formula, right? Okay, but in this formula, what's slightly different? Yeah, you're adding the constant or subtracting the constant from x before you apply the formula. All right, here the formula is applied to x, then we add or subtract the constant. Here you are adding or subtracting the constant from x, and then we're applying the formula or the function. This also is a shift, however, okay, except the shift now is to the left or to the right instead of up or down. Okay, so notice adding a constant to the formula shifts the graph up or down. Adding the constant or subtracting the constant from x shifts the formula to the left or to the right. Now, you have to be very careful about the sign here, though. Okay, if you add the constant to the left, if you add the constant to x, you're going to shift the graph in the negative direction. You're going to shift the graph left. You're thinking, oh, if I add the constant to x, I should shift in the positive direction, but it works backwards. You're going to shift to the left. Okay, if you subtract the constant from x, you're going to be shifting to the right. Okay, so it's kind of intuitively opposite of what you might expect. Now, look, here's why I don't like the book's presentation of transformations. Okay, there are two other big categories of transformations, right? This is the first one. I'm going to show you the other two. These are called shifts. All right. Okay, so there are two basic types of shifts. You can shift the graph up or down, or you can shift the graph left, right. Okay, and you do that by shifting up or down or shifting left or right. Do that by adding or subtracting constant. Now, look, these two shifts, they're both shifts, but in the book's presentation, they look like somehow they're different. They're really not, okay? What's really different is where we're adding the constant. If you think of taking this constant, right, and moving it to the left-hand side. So I'm going to move it over to the left-hand side. Of course, that changes the sign, right? Okay, so if it's plus here, it's going to become minus on the left. If it's minus here, it's going to become plus on the left. Notice that what you're doing in this case is you're adding or subtracting the constant, not from x, but from what? Y, right? Okay, so really these two shifts are really quite similar. It's just a matter of where we're adding or subtracting the constant. If you add or subtract the constant to x, you shift the graph along the x-axis. That makes sense, right? Okay, if you add or subtract the constant from y, you're shifting the graph up and down. Okay, and actually the signs work out the same as well. If you subtract the constant from y, you're going to shift the graph up. You're thinking you should shift it down, but you're going to shift the graph up. If you add the constant to y, you're shifting the graph down. Okay, same thing here. If you add the constant to x, you're shifting the graph in the negative direction along the x-axis. If you subtract the constant from x, you're moving the graph to the right. Okay, so really these two shifts are really identical. It's just a matter of where we're adding or subtracting constant, either X or Y. All right. That's one type of shift. Now, we haven't seen any examples yet, so you have to bear with me till we get to some examples, okay? Let's look at the second type of shift, which is called a rotation, and it's very simple, all right? With a rotation, you're just multiplying by a minus sign, okay? So the way the book explains this is if you apply the minus sign to the whole function, you're rotating the graph around, what does it say here? Yeah, that's right. You're going to rotate the graph around the x-axis, right? So if you have a graph, if you apply a minus sign to the formula, it rotates the graph around the x-axis. So the top part of the part above the x-axis rotates to below the x-axis, and the part below the x-axis rotates up above the x-axis. It's rotating, so you got to sort of think three-dimensional, right? It's rotating around x-axis. All right, now here the book says, oh, if you apply just the minus sign to x, you're rotating around what? The y-axis, right? Okay, you're rotating around, taking the whole graph and rotating it left to right around the, or right to left around the y-axis. Now, again, these rotations are really the same, okay? Because if you take this equation and divide both sides by a minus sign, guess what happens? Well, the minus sign shifts where? To the left-hand side, right? So you get minus y is equal to f of x, right? So what this transformation is really saying is the following. If you multiply the variable x by a minus sign, what happens? The graph rotates around what? What does it say here? The y-axis, right? So if you multiply x by a -1, you rotate around the y-axis. If you multiply y by -1, what happens? You rotate around what? The x-axis, right? Okay, so it's really just a matter of multiplying y by a negative or multiplying x by a negative, okay? If you multiply y by a negative, you're rotating around the x-axis. If you multiply x by a negative, you're going to rotate around the y-axis. All right, so that's the second big category of transformation. That's called a rotation. Here's the third big category, and this is called a stretch. So we've shifted the graph up and down, left and right. We've rotated the graph. The other thing that we can do with the graph is stretch it. So if you've got a curve, you can think of stretching it, sort of pulling it apart like an accordion or something, or you can think of taking it and squeezing it in, okay? This is called a stretch. So you can pull it apart or you can squeeze it in. You can also pull it up in the vertical direction or squeeze it in the vertical direction. So squeezing this way or expanding this way or squeezing in the horizontal direction or expanding in the horizontal direction. That's the third type of transformation. All right, how do we achieve these transformations? Okay, it's the same as before. Let me start with the second type first. If you take x and multiply it by a constant, let's think of the constant as being positive, because if the constant is negative, what's going to happen? The graph is going to what? It's going to rotate, right? Okay, that's the second type of transformation. So let's think of this constant as being positive just momentarily here. If you take x and multiply it by a constant, that is going to stretch or shrink the graph. Okay, so the graph is either in a horizontal direction. If you multiply the constant by x, you're going to stretch or shrink the graph in a horizontal direction. Now, which is it, stretch or shrink? It depends on the size of the constant. So if the constant is less than 1, you're going to stretch the graph. So if the constant is, say, 1/2 or 1/4 or 3/4, something less than 1, you're stretching the graph horizontally. So you're pulling it apart. If it's a constant bigger than 1, you're shrinking the graph. So you're sort of taking it in, squeezing it. You see that? Less than 1 is stretching, bigger than 1 is shrinking. Now, you know, when you're stretching and shrinking something, you're going to ask, well, by what factor, right? Am I stretching it by a 2? Am I shrinking it by 1/2? You know, what factor? And again, that depends on C. So take your constant and put it over 1. That tells you the factor by which you're stretching or shrinking. So if this were 2, just for fun here, that's a common constant. So if we had 2x here, what would we be doing? Let's see. What would the new graph look like? Would we be stretching it or shrinking it? If I replace the C with 2. What does this say?
Would you be shrinking?
It would be a shrink by what factor, Robbie?
1/2.
1/2, right. In other words, okay. So you're going to take the graph and shrink it by a factor of 1/2, right? Now, the other type of transformation is exactly the same, okay? The other type of stretch is exactly the same, all right? They have the constant in this equation, they have the constant written on the right-hand side. But you can move that constant to the right-hand side just by dividing both sides by C, right? Okay, so really, this type of stretch is really the same as this, okay? So my point is, it's easy to understand this last type of transformation. If you multiply the y by a constant, okay, it's the same thing is going to happen as you multiply x by a constant, all right? If the constant is less than 1, you're going to stretch the graph. If the constant is more than 1, you're going to shrink the graph. Except you're not going to be stretching or shrinking horizontally. You're going to be stretching what? In what direction? Vertically, right? Okay, along the y-axis, which is vertical. So if this, again, you can read these instructions just exactly the same. If the constant is less than 1, you're stretching. If the constant is more than 1, you're shrinking. And just take that constant and divide it into 1, and that tells you the factor by which you're stretching or shrinking. So really, all we're doing in these transformations is we're either manipulating the variable y or we're manipulating the variable x, okay? But the results are the same, except the results apply to what? Either the y-axis, right? Where you're stretching or shrinking or shifting vertically, or the effects apply to the x-axis, where you're stretching or shrinking horizontally or shifting horizontally, okay? All right. That seems all kind of a lot to absorb at once, right? But it's very easy. Let's practice it a little bit. So I've drawn a very simple graph here. This graph, whoops. I've drawn a very simple graph here. This is supposed to be square root of x. That's the graph of square root of x. By the way, remember the domain of this function, you cannot have any negative numbers, right, in the domain of this function. So the x here, remember, has to be bigger than or equal to 0, right? So when you draw the picture there, the graph starts at 0, on the x-axis because you can't have any negative x values. All right, so there is what the graph of square root of x looks like. That's a very simple curve. Okay, you know, doesn't have much of a shape to it, but there it is. Okay, it's not a straight line. All right, and now let's see if we can use our knowledge of what square root of x looks like, right? Okay, let's see if we can then, well, quickly, okay, at least without too much work, let's see if we can graph these other functions, which are a little bit more complicated than square root of x, right? Okay, so how do we do that without having to plot points, right? Because we don't want to plot points. Again, how do we use our knowledge of square root of x? This is square root of x to make these graphs. Well, what we're hoping for is that these graphs are just transformations of square root of x, one of those three types of transformations that we just listed. All right, so so let's start there. Okay, so let's figure out what square root of x minus 2 is supposed to look like. Okay, so is that a transformation of square root of x? What are we doing here in changing this formula to this one? There's not much difference, right? What have we done? Yeah, we subtracted what? A 2, and that's important where we subtract the 2. So we subtracted 2 from what? From the x, right? Oh, we subtracted 2 from x. So that is one of the transformations that we just learned. Do y'all recall which one? There's 3 types. So there's shift, rotation, and stretch, which includes shrink. Okay. So which kind of transformation is this? That's a shift, right? Because what did we do? That's right. We subtracted a constant. 2 is a constant, right? So we subtracted a constant from x. Oh, so we have a shift. What kind of shift is it? Yeah, it's either left or right, right? Because we subtracted the constant from x. So that means our transformation is happening along the x-axis, right? Well, things that happen along the x-axis are going to be horizontal, right? So we're shifting this either to the left or the right. Now the question is, which one is it? Remember, if you so it's counterintuitive. If you subtract the constant, what are you doing? You're shifting to the right. Yeah, you think I'm subtracting, so I'm going this direction, right? But actually, it's backwards. All right, you're shifting to right. Okay. So, what does the graph of this new curve look like? Really easy, right? We can visualize it very clearly, right? Without much work. We're just taking this whole curve and doing what? Going to the right. Yeah. Okay. Erase this. Yeah, we're just shifting it to the right. So let me see if I can draw that. We're just shifting it to the right 2 units. So I'm going to start here, right, instead of at the origin. And then I want to draw a curve that's kind of quote unquote parallel to this one. Curves that can't be parallel to one another, right? But want to make it look the same, right? So see, there it is. Just that simple. I know what that graph looks like. Okay. So yeah, now the point here is really not always to help you. Well, sometimes it is. No, I shouldn't say that. I was going to say the point is not to help you draw the graph, okay? But the point is to help you be able to visualize the graph so that you're not always stuck with drawing it. But actually, sometimes our knowledge of transformations will help us draw graphs too, by hand. So this is A, all right? Shift, which direction? Let's fill it in. Where do we go? Right, yeah. Now, what is the second one? See, that still involves square root of x, right? And still we have done what here? What did we just put in? We've added a constant, yeah, okay. We've added a constant. But Hannah, now, we're going to rewrite this formula slightly because really, where have we added the constant? See, that constant is really not added to the x. because you can take this one, here's how, here's how I want you to think of it. You can take this one and do what? Yeah, you can move it. See, this 2 you could not move, right? Because it was under the square root. But this one, you can move it to the left. And what does that give you, of course? Y what? Y minus 1 is equal to what? So really, what are we doing in this transformation? I've subtracted a constant, right? But from what? From X? No, from Y, right? Okay. So that wasn't really clear at first when I had the formula written down. That's why I moved the constant to the left-hand side. What we're really doing there is subtracting from Y 1. And what do you do when you subtract a constant from Y? You shift what direction? Up or down, right? Okay. And it's counterintuitive again, right? Since I'm subtracting, which direction am I shifting? Yeah, I know your intuition is different from what I was hoping it would be. Yeah. Since you're subtracting, your intuition would say, I'm moving down, but your intuition is wrong. Yeah, okay, right? When you subtract a constant, you're going in the other direction. So you're shifting up. Okay. So we're what you expect, right? Okay, yeah, right. So so Emil, what does this curve look like? You can only be wrong, Emil. Yeah, which way am I shifting? Up. Yeah. Okay. Right. You're shifting up. Right. Shift up. So I just shift the whole thing. So this point goes up by 1, right? And then the rest of the curve just goes up. So I have to draw it. You're gonna have to be kind of careful here. Here's what it's going to look like, right? Whoops, in there I really messed up. So let's just take that part off. Yeah. Okay. Just shifted up by. So there is B. Okay. Let's skip to the last one. Okay. And now this one is hard to draw by hand. But the key thing here is just sort of visualizing what's happening. We'll try to draw it, but it's not clear how accurate our drawing is going to be. All right, okay, but we'll have the right idea at least. Okay, all right. So let's think about what is happening. Ooh, what's happening here? All right, let me change this to y. All right, instead of g of x. It's easier to work with y. So you can see 2 things are going on there, right? Okay, I have a what? Constant that's been put in here, right? But this is not added or subtracted. This is multiplied, right? Okay. So what does multiplication of a constant do? Do you recall? What? Not quite. Multiplication of a constant is that's stretching or squeezing or yeah, either, and it could be horizontal or negative. Here, I'm sorry, or vertical. But here, Hannah, I'm multiplying the constant by what? X. So that's going to, which way is that going to stretch or shrink it? Since it's X, that's obvious, right? It's going to stretch or shrink it horizontally along the X axis. All right, let's scroll back up and look. So I multiplied the X by the constant, right? So that means, and that constant is bigger than 1, right? So what did it do? It shrunk it horizontally by a factor of what? It's 1/2 or 1/2. Okay, right. So shrunk it horizontally by a factor of 1/2. So if the graph is occupying this space, that means it's gonna shrink to this. Okay, 1/2 of that. If it were 1/3, it would get just progressively smaller. Now that's hard to draw by hand. You can sort of visualize, okay, I'm squeezing that graph in, but to draw it accurately is not going to be easy, but we need to keep that in mind. So we've shrunk it horizontally by a factor of 1/2. Now, I can't just immediately start drawing because I've also got this minus sign to deal with. This minus sign is not with the x, though. It's outside of the square root. So you can shift that minus sign to the left by dividing both sides by -1, right? So when you do that, what do you get? Minus y is equal to square root of 2x. So notice the minus sign is really on the y, not on the x. So when you apply a minus sign to the y, what does that do? That's a rotation. How? Around the x-axis, right? That is a vertical rotation. So that means you're going to rotate it around the x-axis. Wow. So let's see. I rotate it around the x-axis. So there's the original graph. It's going to get rotated around the x-axis. So all of this is going to get rotated down, okay? And shrunk by what? A factor of what? 1/2. So this thing is going to get shrunk by a factor of 1/2. Oh, well, let's see if we can draw that. Let me draw it down here. No, this is still not good. Okay, I didn't leave myself much room. All right, let me erase this. Did not plan ahead there. So, wow, what's that going to look like? Rotated down and shrunk by a factor of 1/2. Would that end up looking, gosh, that would look something like this, maybe? I'm drawing it really poorly. It's clearly getting, y'all understand the rotation? You're flipping it around the x-axis, okay? You're rotating around the x-axis. So sort of lay your hand there above the x-axis, you're rotating it like this, right? Okay, so this graph is rotating down, but it's not going to look exactly the same because it's getting shrunk in the horizontal direction. So by a factor of, I'm thinking 1/2. So here's the extent of the curve before. Now the extent of the curve is going to be like 1/2 of that, right? Okay, it's going to look something like this. Shrinking and stretching is not the easy thing to imagine. Okay, shifts you can imagine pretty easily. Shrinking and stretching, that's hard to imagine. What's the one I left off? 2 times the square root of x. So see there, I have another. This is not 2 plus square root of x, right? This is 2 times square root of x. So again, what I've introduced here is a constant. Not that I'm adding or subtracting, but instead I'm doing what? What am I doing with the 2 there? Yeah, I'm multiplying, right? Okay, I'm multiplying. But the 2 is not multiplied directly times the x. You can actually now move the 2 to the left-hand side. How do you do that? Divide by 2. So if you divide by 2, you would get, I'm going to write it this way. That's y over 2, but I'm going to write it as 1/2 times y equal square root of x. Now it's more clear what's happening, right? I've multiplied the y by what? 1/2. So what is that effect going to be? It's going to be a stretch of some sort, right? Let's look back and see what kind of stretch that's going to be. See, when you multiply constant times y, right? You're stretching or shrinking. Don't read these instructions. Read these. They're the same. So we're stretching or shrinking, but it's vertically. Is our constant bigger than 1 or less than 1? 1/2 was what? Less than 1, right? So we're stretching, right? Okay. So we're stretching and we're stretching vertically. All right, not horizontally because the constant is multiplied by y. By a factor of what? Not 1/2. It's 1 divided by 1/2. What's 1 divided by 1/2? 2. Yeah, okay, right. Let's put all that together. So we did we stretch it, right? Stretch it, right? Vertically by a factor of what? 2. Stretch vertically by a factor of 2. Wow, what do y'all think that would look like? So here's the original graph. We stretch it vertically by a factor of 2. What effect does that really have? It makes it not longer, but taller. Yeah, okay. By a factor of 2. So I think it's going to be something like this, right? It's going to go like that. It's getting stretched up by a factor of 2. It's going to make it longer. Be nicer if we had some wiggles in here. That makes the stretches easier to understand. But here with just a straight curve, I'm pulling that curve up somehow by a factor of 2, right? So it's going to go up much faster. It's going to be taller, just as y'all told me. All right, so let's see. This one was D, right? This one is D. Okay. Woo. Let me make it easier. All right. So here we have some functions. I'm not even going to make a graph of them. Okay. So one of them is absolute value of x. That's pretty easy to graph, though. One of them is x squared, and one of them is e to the x power. Now that's a little bit tougher to graph. Okay. E, by the way, that's an irrational constant. That's like pi. So you may have heard of that number before. That's an important irrational constant in calculus. You know, pi is important in geometry and trigonometry, right? But in calculus, this irrational constant E is very important. It's approximately 2.718, but it's irrational. So it's a non-terminating, non-repeating decimal. To 3 decimal places, it's 2.718, okay? So we're taking that base, 2.718, and we're raising it to x, right? Whatever input x is. All right, so you can graph that function. It gives you a pretty simple curve. And x squared is a basic curve, and so is absolute value. All right, so here's what we want to do. We want to take those graphs that we get from those 3 functions, and I want to perform the following transformations. Wow. So I want to stretch it vertically by a factor of 2, shift it left 1, and then shift it up by 3 units, okay? Stretch it by a factor of 2, shift it left 1 unit, and shift it up 3 units. So whatever graph I get for absolute value of x, this is transformations I want to apply. What would the new formula look like? Not what the graph looks like, but what does the formula for this new function look like that's been transformed like this? Let's start with the easy part, the shifts. Those are pretty easy, right? Okay, so how do we shift to the left 1 unit? You would add, right? Okay, but where do you do the addition? To what? To the left. Yeah. We're starting with this one. So what now? Yeah, inside the absolute value bars. Okay, right? Yeah, this is absolute value bars. Yeah, you're going to, since you're shifting to the left, you're going to add 1, right? And you do it to the x. So right with the x inside the absolute value bars, that's where you add, okay? So your formula is going to start off by looking something like this, okay? When you shift to the left, you're adding 1. Since it's to the left, you're going to add the 1 to the x. How do we shift up now? 3 units. Subtract, right? Okay. But Amanda, now where do we do the subtraction? From, see, this is up or down. So that applies to, from what? No. From y. Okay. Remember, f of x is the same as y. All right. Oh, so I've got to fill in the f of x now. So I have f of x, right? And you just told me, Amanda, what do I do? Subtract. Right. Okay. So now I have to write the equation because I'm going to subtract 3 from y, but y is the same as f of x. What's the last thing now? Stretch it vertically by a factor of 2. So when you're stretching vertically, a stretch means you're not adding or subtracting a constant, right? You're doing what? Multiplying, right? Okay. So you're multiplying. Where do you want to multiply? Yeah, so when you're stretching vertically, are you multiplying x by something or y by something? Y, right, okay. So y here is the same as f of x, right? So I'm going to multiply f, let me rewrite this. So I'm going to multiply f of x by something, correct? But now the question is by what, right? So I'm going to multiply the f of x by something. What's that? Something. Yeah. 1/2, right? Okay, because we're stretching vertically by a factor of 2. Reciprocal. So we multiply by 1/2, right? There we go. Right. What now? Would be 1 over. Yeah, it's 1 over 2, right? Because 1 over 2 is 2. If you want to now, you can take this and solve it again for f of x. Okay, all right. But that's the idea there. What about x squared? Same transformation. So what's it going to look like? When you stretch it, you get what? How do you stretch it there? Multiply by 1/2, right? So y gets multiplied by 1/2, right? Okay. And then what? How do we shift it? -3, right? And then how do we shift it left? You add 1 to x, right? Be sure now when you add 1 to x, you do that before you square it. All right, so do that before you square that. What about for the e to the x? Same thing, right? except how do you add 1 to x here for e to the x? That's right, it's e to the x plus 1. Okay. Don't write the plus 1 here. Don't write it like this. Because if you write it like that, what have you really done? What sort of transformation have you done there? You moved it up or down. That's right. Okay. Really haven't moved it left or right. To move it left or right, you have to add the 1 directly to the x. Not down here, but directly to the x in exponent. Okay. All right. All right, let's wait a minute and then we'll come back. And here's a graph, original function called g. And I want you to tell me, original function called f, which is the absolute value of x. So there's the absolute value of x. That's this V-shaped curve, right? So, but now we have this new function g, which I claim is just a transformation of f. Let's see if we can write down what the formula for g is. All right. So there's the graph of g. That's a transformation of this original function f. May have several different transformations in it. Okay. But let's see if we can write down the formula g, right? Based on f, which is just absolute value of x. All right, let's save that till we come back though. So let's come back at 11:30 and then we'll see if we can write that one down. See if we can figure out what those transformations are. Okay, I resumed. So let's look at absolute value of x here, which is this graph f. So that's that V-shaped curve. And then squeezed in here is a transformation of f, right? So you can see, right, it looks like it could be a transformation, right? It's got the same basic shape as f, right? Except it's a slightly different. So we want to see if we can write down a plausible formula for that new function g, if it really is just a transformation of f. So we're just trying to look at how does g differ from f, right? And what transformations could we apply to f that seem like they could give us g? And then we'll test it and see if we really got the right answer. It's hard to know without testing it. Let me rewrite f first here, though, as just at y equal absolute value of x instead of f of x equal absolute value of x. Just to make it maybe easier for us to experiment. So how does g look like f? I mean, or how does g look different from f? What's happened with f possibly there to give us g? There hasn't been a rotation, right? Because if there are, well, I guess there could have been. There's not a rotation around the x-axis at any rate, right? Okay, because if you had a rotation around the x-axis, your v would open down instead of up. I guess you could have had a rotation around the y-axis, because if you rotate f around the y-axis, it looks the same, right? Okay, think about that V-shaped curve. If you rotate that around the y-axis, the left side of the right side of the V is going to become the left side of the V, and the left side of the V is going to become the right side of the V. So you wouldn't be able to really tell. So, well, that's kind of meaningless there to think about that. So, but what has happened, kind of obviously, it's been shifted down, right? So you really have to squint, but F there has this, by the way, this is a local minimum, right? Okay, so F has a local minimum there at the origin. It's got a turning point there at the origin, right? Because it shifts from decreasing to increasing. But on G, that's been shifted down, right? Okay, so it looks like we've had a downward, it looks like there we've had a downward shift, right? That's pretty easy now to write down, because what's that downward shift going to look like? Just what? Is it a minus, or is it a plus, or what? It's a plus, right, to shift it down. And it's a shift of 1. So it looks like we're adding 1, but to which variable? Y, right, okay. So we have y plus 1 there now is absolute value of x. So the first thing I'm going to do now is, I should have cautioned you about this before. Once I have decided there's this shift, right, and I'm going to move it down, let's this gets a little bit tricky. No, that's fine. Let's just leave it like this. Okay. All right. So there we have y plus 1 there is absolute value of x, right? Okay. And now what? Yeah. There's going to be a shrink there, right? Okay. So because it looks like we've taken the graph of f and just done what there? Just compressed it, right? Okay. So so it looks like there's a horizontal, it looks like there's a horizontal shrink, which means I've done what? So for horizontal, we're doing something to which variable? X, right? Because that horizontal is along the x-axis, right? Okay. For a shrink, though, what are you doing with x? You're not adding or subtracting from x, right? That's going to give you a shift. So for a stretch or a shrink, you do what? Multiply, right? Okay. And so now we just have to figure out what's that constant, right? That we're going to multiply by x. And now that kind of gets a little bit iffy because we're trying to think of, you know, how much are we shrinking this by? Okay. Any guesses there? 1/3? Emil, is that what you're thinking? Oh, who said that? Okay. You're saying 1/3? Which means what would I put there for that constant? 3. Oh, so he's thinking it's 3, right? Which would give us a shrink by 1/3. Okay. All right, now, so now let's move the 1 over. So we have y equals to this. And shall we test that? Okay. So let's try it and let's see what happens. So if I plug 0 in for x, right, you get absolute value of 0, which is 0 minus 1 is minus 1. So you get this point. So that much is correct, all right? Now let's try here 1, all right, and see if that works out correct. So y equals to absolute value 3 times 1. Whoops, absolute value 3 times 1 minus 1. How much is that? 2. Is that where we're at here? Yay. Okay. Oh, so you're looking carefully there. All right. At least so far. All right. So because that point matches, right? Okay. At 1, we're here at 2, and that's on G. Let's try 2. If we get 2, then we'll probably be happy there, right? So absolute value of 3 times 2 minus 1 is what? 5. Is that correct? Yeah, we got that one too. All right, so there it is. Okay, there's the formula for our transformed G. Absolute value of 3 times x minus 1. You want to, you can write that as G of x. Well, okay, so those are kind of good, kind of fun examples just to learn about transformations, but in practice, they're probably not all that useful. But what is going to be useful is applying transformations to these trigonometric functions, okay? Because the trigonometric functions are not going to be at all easy to graph, and so transformations applied to trigonometric functions are really going to be helpful to us in understanding their graphs. here's one fact that I think we'd already kind of discovered, but we're going to sort of restate it here in terms of transformations. So it says the graphs of sine of x and cosine of x are given here. Sine of x is the blue curve. So here's the sine wave, right? You know, it's got lots of wiggles in it, right? So you have lots of local maxima and lots of local minima on the sine curve. And then graph next to it there is the cosine curve. So the red curve is the cosine curve. Well, notice that the sine curve and the cosine curve have really the same shape, right? Okay, they're really the same curve, except what's happened? They're shift, right? That's right. One is just the shifted graph of the other, right? Okay. Of course, a shift is just a transformation. So really notice that the sine and the cosine curves are just transformations of each other. So what we want to do here is write the sine curve as a transformation or a translation. We want to write the cosine curve as a transformation, or also sometimes called a translation of the sine curve. All right. So in other words, I want to write cosine of x as some sort of shift, right? We can see it's going to be a shift of sine of x, right? So what would that transformation look like? Well, pretty clearly here, right? We're shifting in which direction? See, this is the blue curve, right? So you're there's more than one way to think of it. I should be more explicit. Let's think of taking the blue curve and let's move this point back to this one. See, if you move this point back to this one, right, then the blue curve would just overlap the red curve, correct? Okay. You could have also thought of moving in this direction as well. All right. So let's so that would also work, but let's think of taking the blue curve and shifting it back. So that's a shift to the, obviously to the left, right? So that means, how do you achieve a shift to the, what do you add to x, right? So we're going to add some constant to x, right? Okay. We just had to figure out what that appropriate constant is. In other words, how much is this amount, right? Okay. In this picture here. What's the length of this arrow then, in other words? Now, be careful. We want to be careful to write that down right. So we know that cosine is a shift of sine, and we're going to add a constant to x, but that is not the correct way of writing it, right? Okay. If I put there sine of x plus c, of course, I got to figure out what the right amount for c is, correct? But this is not going to be the proper way of putting it down, because what sort of shift is this really? That's a vertical shift, right? Because think, you can take the constant in this case and simply move it to this side, right? That's the side where y would be. That would make it a vertical shift of some sort. So you cannot just take the sine of x there and figure out what this constant is and add it on. What do we need to include here? Parentheses, right? I need to make sure that I'm adding my constant to x, not to y. All right. So in writing down the formula, need to have parentheses around the x and the c. Otherwise, you're going to end up with a vertical shift. Okay, well, now that's so I'm going to end up with a formula that looks something like this. Just got to figure out what the c is. So in other words, what's this distance? Well, this is pretty easy to figure out from our knowledge of special angles, right? We know that the cosine curve at 0 begins at what? 1. But the sine curve doesn't hit 1 until what value? So sine starts at 0, right? And it goes up. Remember, at pi over 6, it's 1/2. At pi over 4, it's square root of 2 over 2. At pi over 3, it's square root of 3 over 2. And it doesn't max out until where? Pi over 2, right? Okay. So this point here is on the x-axis is pi over 2. That's where the sine curve hits 1. That's also where the cosine curve hits 0, remember? Okay. So so this distance is pi over 2. Oh, so my right formula is what? Sine of x. And then we're going to the left. So I do what? Add, right. So there it is. So cosine of x is really the same curve as sine of x, right? It's just this transformation by shifting the sine by pi over 2. Now I'm going to give you guys some to play with. Here's the first one. So there's the graph of sine. That's just plain old sine. All right. And here is a second curve that is a transformation of sine. All right. Transformations of the sine curve are called sinusoidal functions. So they're not quite the sine function, but they're transformations of the sine function. So they get a special name. It's kind of more complicated. It's sinusoidal. All right. So here is a sinusoidal curve. It's a transformation of the sine curve. So cosine is an example of a sinusoidal curve because it's a transformation of the sine curve, right? Any transformation, therefore, of the cosine curve will also be a transformation of the sine curve. So any transformation of the cosine curve is also called a sinusoidal function. So here's your first example of a sinusoidal function. Write down its formula. So what does that formula have to be? What is that transformation? There's the original sine curve. There's a transformation of the sine curve. What have we done? Get from here to here. Okay. Just write it down. Yeah. So this is what y'all just try on your paper. What? Attendance. Oh, okay. So while you're writing that down, You see what it is? Say what? Stretch it. Stretch. And stretch. 5, 3. Vertical. What? What sort of? And start. Are you shrinking it now? But just look at it. On A. Stretch like that. Yeah. Hi. Yes. I can see y'all are a little bit slow on this, all right? So let's take a look at what's happening on this curve. So that's the first thing you have to do is look at it, right, and think about it. So how is this curve different from this one? They are not, it's not stretched horizontally at all, okay? Because look, of course, this one starts at 0, this one starts at 0, and then it makes one full cycle here, right? Okay, right, one full period here, right, goes up, down, and then back up again. That is the same length here as it is here, slightly more than 2 pi, right? Okay, think about what happens to sine. It makes, it goes through all of its values, right? When you go through one full revolution on a circle, correct? Which is 2 pi, right? So the same thing happens with this curve, right? It goes through all of its possible values there between 0 and a little bit more than 6, which is 2 pi. So this has not been stretched at all vertically, okay? I mean, stretched at all horizontally, right? But of course, it's not the same curve because we have indeed changed it. How? Yeah, we've stretched it vertically. The normal sine curve maxes out at what? 1, and its minimum is -1. So sine has an absolute maximum of 1. It never gets above 1 on the y-axis, and it has an absolute minimum of -1. It never gets below -1 on the y-axis. But this one goes up to 3 and goes down to -3. So this one has been stretched by a factor of what? 3, right? It's been stretched vertically by a factor of 3. So how do you write down a transformation that stretches vertically by a factor of 3? It's a vertical stretch, so we're going to be changing what variable? Y. But don't put a 3 here. That would be the first thing to think of, right? Okay, I'm stretching vertically by a factor of 3, so I'll put a 3 there. But that actually means you're stretching it by a factor of what? 1/3. So that would shrink it. Okay, right? What do you really want as the constant there? 1/3, right? The reciprocal of 3. You're stretching it by 3. So here you put a 1/3. Now, look, let's solve it for y again. In other words, let's get rid of the 1/3. So how do you get rid of the 1/3? Multiply both sides by 3, right? When you multiply both sides by 3, you get y equals what? See, well, wow, that's so easy, right? So stretching it vertically by a factor of 3 just means I multiplied the sine x by what? 3, right? Okay, so there's the formula for this curve. It's 3 sine of x. Because it was just stretched vertically by a factor of 3, I just get 3 times the sine of x. This maximum height on the sine curve is called its amplitude. All right, it's amplitude. And that's kind of a physics name for that maximum y value. So the amplitude of this sine curve is 3. The amplitude of the normal sine curve is what? 1. You can change the amplitude just by multiplying outside of the sine by whatever amplitude you want. Okay, in this case 3. If you put the 3 by the x, so if you had sine of 3x, that is different. These two things are not the same. And how is that different? What does putting the 3 here by the x do? That's also a stretch, but what kind of stretch? Horizontal, right? Okay, that's a horizontal stretch. So it's going to change the way the curve looks from left to right. And in fact, what would it do? What does this do? It's going to shrink it by a factor of what? 1/3. So this curve is going to get shrunk by a factor of 1/3. When you shrink that by a factor of 1/3, then what happens to it? It starts wiggling a lot more, right? You're going to see a lot more wiggles. Okay? The curve has been compressed horizontally. When you compress this curve horizontally, remember there are a lot of wiggles on the left and on the right. You're just not seeing it, right? So when you compress it horizontally, you're going to start seeing the curve. You're going to start oscillating much more. Right? If you stretch it out horizontally, it doesn't oscillate fast, right? Okay. Well, let's try another one. Maybe this one has changed the oscillation. Maybe not. All right. So have we changed the oscillations here at all? Is this one oscillating faster? I'm looking at B. Is this one oscillating faster than before? Look at how long it takes to go through one cycle, one full period. Let's start here at 0 on the x-axis. So normally the sine curve does what? It goes up to its maximum, it comes down to its minimum, and then it goes back up to 0, right? How long does that normally take? 2 pi, right? Which is a little bit more than 6, correct? Okay, because 2 pi is one full revolution of a circle. Let's see, is that what's happening here? That's what happens in the normal sine curve. Is that what happens in this sine curve? Yeah, it goes up, comes down, goes down to its minimum, comes back up. And where does it get back up to? It's sort of where it started from, right there, right? And where is that from best we can tell? That's a little bit more than 6, right? Which is probably 2 pi. So this has not been compressed, okay? This has not been compressed, at least not, or stretched, at least not horizontally. Has it been stretched vertically? No. Okay. It's been shifted, but it hasn't been stretched, okay? What's the distance in the normal sine curve? What's the distance between the maximum and the minimum? Its minimum is what? Its minimum is what? -1. Its maximum is what? 1. What's that distance between -1 and 1? 2, right? Okay. So it's distance 2, right? From the peak to the valley is 2. Is that what happens here on this curve? There it is at the top. What's its top? At what? At bottom, it's what? 2. That's a distance of what? 2 again. So it's not been stretched at all. Okay? Vertically, it's not been stretched or shrunk. Okay. It's still distance 2 from the top to the bottom. Horizontally, not been stretched. Oh, because there's not much left we can do except what? We haven't stretched it. So what are other possible transformations there? Shifted, right? Okay. Fernando, you think it shifted? What would you say the formula is here? Yeah, you're right. Y minus what? Is it gone up? Yeah, 3, right? Equals what? Sine of x, right? Okay. Now just solve that for y. So you have y equals what? There you go, right. Okay, so to shift it up, we just do what? What does it look like here? We did. Just added 3, right? Okay. To shift it up by 3, we just added 3. Here, to change the amplitude to 3, we just did what? Multiplied by 3, right? Okay. To shift it up 3, we just added 3. Easy. Oh, let's now try this one. Okay, so I'm going to let y'all think about this one. Pretty clearly what's happened on that one. That has been something horizontal, right? See, there's a sine curve with normal oscillations, but what's happening to this one? It's oscillating much more quickly, right? Okay, because you get a lot more wiggles from 0 to 2 pi. You get a lot more wiggles here than you got here. That means it's been shrunk. That means it's been shrunk, right? It's been compressed in the horizontal direction like this. So how much do you think it's been compressed? See if you can write down the formula. It's the amplitude, though, has not changed. So it's not been stretched horizontally. It still goes up to 1 and still goes down to -1. So it's not been stretched vertically, I mean, it's only been stretched horizontally. Okay. All right. So what's the horizontal stretch, and see if you can write down. Okay. Make sure you get the constant. Make sure you get the constant rise. Okay. Remember, it's tricky for a stretch because reciprocal is what you expect. How much has that been compressed by a factor of what? Anything? What do you think? Just give us I think it probably. Look, how many cycles? Oh, okay, that's. But normal. Go to 2 pi. One side. Wow. 2. By factor. That's right. Yeah. All sort of converged on something, getting the numbers lined up that's really getting the right constant. Okay, let's see if we can write something down. All right, before we run out of time. So everyone sort of agreed, right? That what's the transformation that we're doing here? Shrink it in the horizontal direction, right? So we shrunk it in the horizontal direction. So when you shrink in the horizontal direction, right? How do you express that in the formula? You multiply x by something, right? Okay, so we have to have here our x multiplied by something. We just have to figure out what that right constant is, correct? Okay, now that constant depends on if you're shrinking or if you're stretching, right? We already decided we're shrinking here, and correct, by what factor we're shrinking. Now, let's first, by what factor are we shrinking here? By a factor of, that would be a factor of what? 2, right? Okay, because let's see, the original sine curve, right? Okay, goes through one cycle, one period from 0 to 2 pi, right? But this one makes it through 2 periods, right? From 0 to 2 pi. This is 2 pi, right? See, normally the sine curve goes up, down, up again from 0 to 2 pi. This one does that cycle twice, right? From 0 to 2 pi. So we can think we're shrinking it here by a factor of 2. Okay. So what should the C be? Let's check ourselves here. So let's scroll back up in the notes and see if we can decide. All right, so there it is, right? Okay. And did we decide we were shrinking or were we shrinking? Right. Okay. So we have to have a constant here bigger than 1. All right. So that means our description there was a little bit off. I said we shrunk it by a factor of 2, but actually the way we want to describe that is we shrunk it by a factor of what? 1/2, right? Okay. So we're shrinking it, and we're thinking the C value here must be, we're thinking the C value must be 2, right? Since we have to pick a constant bigger than 1 to get a shrink. So pretty easy again, right? Okay. Or a pretty easy formula. Just y equal sine of 2x. So make sure you have the 2 there next to the x, right? Because if the 2 is outside, then what are you changing? Right, okay. In other words, you're going to change the height of the sine curve. You're going to change the amplitude of the sine curve, which normally is 1. Normally, we just go up to 1 on the y-axis. If you put the 2 here, you'll go up to 2 on the y-axis, okay? Unfortunately, what we didn't do here were any, we didn't do any horizontal shifts. And those are fun with the, those are fun with sinusoidal curves, okay? So we'll get to those eventually. All right, we're gonna stop there for spring break. So I am gonna post some homework on transformations. I don't know how hard it is. Right. So the homeworks that's posted are what are due over spring break. Okay, guys, I'll see y'all in a week, right? Okay. A week from Monday. Enjoy your spring break.